Yeah, good morning. Let me first thank the organizers for the opportunity to be here and talk about a major project on climate change and water resources in Austria. And I'm presenting these slides on behalf of the project team. My affiliation, I'm a professor, chair of hydrology and water resources management at the Vienna University of Technology. Climate change has come up a couple of times this morning. Increasing air temperatures, and this is a global data set of clearly increasing air temperatures in the past 3 decades. If we look at the Alpine region, European Alps, we see that in the past 30 years, air temperatures have increased twice as much as those at the global scale. So changing air temperatures are very real. What about rainfall, which is more important to water resources? We have had significant fluctuations over the past 160 years, as this data set shows, with sort of increasing precipitation in the past couple of years in most parts of Austria, but we will see more details about the regional patterns of precipitation trends in Austria. What is important when we look at trends of rainfall and any other quantity actually is what is the observational window. So if we only look at the past 30 years in this slide, this would indicate increasing trends. But of course, rainfall and by the same token temperatures and other quantities have always varied a lot. So the observational window of our data set is extremely important. Now these were temperatures and precipitation measurements over the past 160 years. What about the future? This is a summary of the IPCC ensemble simulations of the greater Alpine region. The gray shades are the ensembles of a couple of dozen global climate models. The red lines are the predicted or median value of, on the left slide, summer precipitation, on the right side, winter precipitation. The green lines, these are the observations for comparison. So what we see here is really in the next 20 years or so, probably very little will change. Then from 2040, for example, summer precipitation may decrease. The other very important thing here is the huge spread of the simulations. So this is not the error of the simulations, it's the difference between different models. The errors, the predictive errors, are likely larger. So we need to keep in mind when we talk about projections of future climate, then that precipitation is highly uncertain. Air temperature is more certain, and this has very important implications for water resources. I'm here to talk about the results of a major study of Austrian water resources with relation to climate impact and climate effects. So this was a study commissioned by the Federal Ministry of Austria and by all the federal states. And the objective was to assess the climate change impact of the Austrian water resources in the past and make projections for the future, propose adaptation strategies, and deal with all areas of water resources: floods, low flows, runoff, glaciers, sediments, water temperatures, groundwater, lakes, water quality, water use, hydropower. You see quite an ambitious goal. And I will speak about 2 areas today, about runoff and groundwater. The philosophy of the study was slightly different from what the usual philosophies of this kind of studies are. The usual approach is to run GCM, downscale it with a regional climate model, and then run it through some sort of hydrological model in a scenario approach. And then we come up with lots of colorful pictures, which we can trust or cannot trust, depending on our inclination and our approach to science and water management. The difference of this study was that we explicitly highlighted what of the results are trustworthy, which we called hard facts, and what kinds of results are more speculative, which we called soft facts. And in essence, anything that is related to air temperature comes out as hard facts. Anything that is related to water, to precipitation, comes out as medium facts. and things that are related to extremes, like floods, are often soft facts. But there's more subtlety to this. So this was one part of our philosophy, so treating hard facts, soft facts separately and highlighting the result depending on the part of the water cycle. The second part of the philosophy was the scenario approach alone is highly uncertain, particularly for rainfall, particularly for extremes. And in order to give more credibility to the study results, we tried to use more than one approach. Of course, to apply the scenario approach, but to go beyond it wherever possible. We not only run scenarios, we also did trend analysis and a number of new methods, like trading space for time and elasticity. I will talk about this later, which are complementary approaches to the traditional ones and help put more confidence in the results of the study. Some of the results. Annual runoff trends in Austria. You know, Austria 500 kilometers across, and the blue dots are increasing trends in stream runoff. The red dots are the decreasing trends. The big ones are significant. The little ones are not significant at the 95% level. And each point is a stream gauge. These are all measurements, and we see over the past 30 years, we have decreasing trends in the south of Austria and increasing trends in the northern fringe of the Alps. Why is this so? Partly related to rainfall. Here are the trends in the rainfall on the bottom left side. Not really well explained by meteorological models for the same time scale, so they do not very well in simulating these trends. But it's also related to increases in evapotranspiration, as we're able to show. Now, if we look at a different time window, the past 60 years, slightly different, smaller trends, as you would expect if the observational window is longer, and quite a visible decrease in runoff in the south of Austria, clearly related to trends in precipitation. What about seasonal differences? Seasonal differences are more pronounced. You look at the south of Austria, decreasing spring runoff, summer runoff, including winter runoff, actually, and increases in autumn and summer runoff at the northern fringe of the Alps. So this was the past. What about the future? So we applied the traditional scenario approach with a CLM model, which is a regional climate model, downscaled from a global model, and then we fed the results of the climate model into hydrological models, which we properly calibrated to the streamflow data, and then we did a delta change analysis, where we looked at the likely changes in the runoff over the past, the difference between the past 30 years and the future lead time until 2050. And what we see is one of the results, which shows really the differences are quite small. They are probably less than 10%. However, I need to emphasize this is the expected value. This is when we take the average of all the ensemble simulations of rainfall. This is what we would get for a future scenario. But the uncertainty range, both due to the climate model and due to the runoff model, it's much bigger than these 5 or 10%. There are bigger differences of predicted runoff for different times of the year. You see increases in winter runoff, particularly in northern Austria, decreases in summer runoff. Red is decrease, blue is increase. So bigger differences what the seasonality concerns. Now this was scenario, quite traditional. Now the new thing, 2 new approaches. One is an approach we call elasticity approach, where we look at the sensitivity of observed runoff, the temporal fluctuations of observed runoff to the temporal fluctuations of rainfall and air temperature. No model, only data looking at temporal fluctuations. And from this you can back calculate the sensitivity, which we have done here. So you see here on the horizontal axis a percent change in precipitation, on the vertical axis percent change in air temperature. And you just go into this diagram, and then the red circle shows if you have an increase of 5% precipitation, for example, and 1.5 degrees centigrade air temperature, then the runoff will probably not change very much. Blue, again, it would be increase in runoff, red, and decrease. And you can go into this diagram with any predicted or envisaged change in precipitation and air temperature. Only from data, no model. Second new approach is what we call trading space for time. So here we are not looking at the temporal fluctuations of rainfall and runoff and looking at the sensitivity of that. We're looking at the spatial fluctuations of rainfall and runoff. Again, data-based. It's not a scenario-based approach. And we can do a similar thing. So each panel has a different increase in air temperature or a change in rainfall. For example, this panel here in the middle shows a temperature increase of 1 degree. N stands for precipitation. 1 degree centigrade increase in air temperature plus 5% rainfall increase, then we get a slight increase in runoff. But on the top right-hand graph, if you have a plus 2 degrees in air temperature, minus 5% rainfall, you would get decreases in runoff of up to 35%. And then we can compare these different approaches and see where they are consistent, where they're not consistent. And where they're consistent, we can be led to believe that these are more reliable facts than when we have contradiction between different approaches. And you can see in the southeast of Austria, most of the approaches actually show decreasing trends. So this is clearly the regions in Austria where effects of climate change on water resources are more delicate, where more care needs to be taken to look at potential climate impacts. While, for example, in the Alpine region, north of Austria, the sensitivity is much smaller and the methods are not as consistent, actually. Okay. Let me come to the second part of my talk, now groundwater. Of course, groundwater, surface water is closely related, and also the rainfall that feeds into runoff is the main driver for groundwater recharge. So they're closely related, and now a couple of analyses of groundwater. Let's first look at the groundwater trends over the past 30 years in Austria. Again, red is decreasing trend, blue is increasing trend, and the little circles without a color are the insignificant trends. And what we can see here, most of the stations do not show any significant trends, but we do have stations with trends, and I will highlight them in more detail in the next slides. Two examples. First example, a groundwater piezometric station with decreasing groundwater levels in the south of Austria. So we have a drop in the groundwater levels of around a meter in the past 30 years. Unteres Murtal. Another example, increasing evolution of the groundwater levels near Vienna, a couple of kilometers south of Vienna. So what are the reasons of these changes in the groundwater level? Of course, groundwater level fluctuations have many reasons. Climate is one of them, land use is one of them, but there are also hydraulic structures and other water resources management activities that affect the groundwater fluctuations and trends. And we have checked the groundwater stations when we did the trend analysis to make sure, to the extent possible, to focus on those stations where we can see climate signals. Now, two maps in more detail. This is the area of Vienna. So on the right-hand side of the slide, we have the boundary, the border to Slovakia and to Hungary. In the center of the map is Vienna. What we can see is this aquifer, südliches Wiener Becken aquifer, which flows from the southwest to the northeast. And particularly in the south of this aquifer, we see significant increases in the water levels of the aquifer. Why is this? This is because of the rainfall, and we can correlate these trends very well with rainfall. While in other parts of this map, it's not necessarily climate. You have here in the east decreasing trends at the border of Hungary. This is not very closely related to rainfall. So management activities are probably more important. Similar here in the northwest of this map, along the Danube, there are probably other effects that are more important for changes in the evolution of groundwater levels than is climate. Second example, in the south of Austria, the Mur Valley, and we can see quite a diverse set of trends, quite a number of decreasing trends, but also a few stations that have increased, and some of the decreasing trends are indeed consistent with the trends of rainfall I've just been showing a couple of minutes ago. Now, an important issue, groundwater temperature. I said, the climate predictions of rainfall are quite uncertain. Extreme rainfalls are extremely uncertain, but the predictions of air temperatures are much more reliable. And the same applies to the signal if we look into the past. The temperature signals we see in water, both in the groundwater and in the surface water, are very real. We also looked at surface water temperatures, and I'm not showing those here, but we get a very clear signal of increasing water temperatures, both surface and subsurfaces, and quite closely related to air temperatures. Of course, the surface water temperatures are better related to air temperature than is groundwater, because the groundwater systems were often quite locally controlled in terms of the flow system. This graph shows a station in the south of Austria. The blue line is groundwater temperature, and the purple line is the air temperature. And we see the co-evolution of these two variables. Of course, water temperature is more dampened because of the dampening effect of the subsurface, but the general evolution is similar. And we can now use this co-evolution of air temperature and groundwater temperature to infer the sensitivity of groundwater temperature to changes in the climate in a statistical sense. Of course, if you want to know it in detail for a particular study, you would like to run like a coupled groundwater thermal model to account for all the local boundary conditions. But in a statistical sense, we can do this, and did this for all of Austria. And this is the results we get. Let me first show the trends in the groundwater temperatures. We see essentially in all the stations in Austria, we have increasing trend. Actually, the label is wrong, right? These are all increasing trends. Yeah? In this case, the red and orange points are increasing trends in the groundwater levels. And we can correlate these trends with the air temperature. And look at the sensitivity. So the color code is here. But how much would groundwater temperature increase for each degree increase in the air temperature? That how sensitive is it? And the red dots, there are the range of around 0.7 degrees centigrade increase in groundwater temperature for 1 degree centigrade increase in air temperature. And you see most of the points are actually in the red range. So it's slightly less than 1, the sensitivity, because of the dampening effect. But it's in a similar order of magnitude. And a couple of stations, they have different sensitivities because it's not just air temperature fluctuations that controls the system, but also the boundary conditions of the flow system, of course. So, let me come to the conclusions of my presentation. Climate change impacts on the runoff. With all the conclusions, we're looking how trustworthy are the results, and we label them as hard facts, or soft facts, or medium hard facts. And the fact that natural variability is larger than climate change effect applies actually at most scales of water resources. More so if we look at extremes, if we analyze floods and low flows, then the natural variability signal is very strong. And the more we move to larger areas and larger time scales, like averages over decades, the less natural variability becomes because it averages out, and the more the relative effect of climate change becomes apparent. But if we look at the variability between years, which is an important quantity for water resource management, then the natural variability is indeed very significant relative to climate change effects. If we look at the expected value of runoff for Austrian catchments, then the expected changes are quite small, a couple of %, but these are the expected values. These are not the real values. They can be larger or smaller, but here we are really at the limits of the predictability. These are the limits of predictability. It would not be correct to state, to put more confidence to this and saying these are like plus minus 5% are the confidence bounds. They're not. The confidence bounds would be significantly wider. But the expected value is not very large. Then we can look at the southeast of Austria. These are the low rainfall regime catchments in Austria. And these are also those that are more sensitive to possible changes in air temperatures, or likely changes in air temperatures and possible changes in the rainfall regime. And it's quite possible that runoff in these areas will decrease, mainly because of increases in the evapotranspiration. So assuming precipitation will not change much, the climate model says it will increase in the area a little, but let's assume it does not increase too much, then the evapotranspiration, the enhanced evapotranspiration, because of the larger energy supply, will reduce the runoff slightly. Then the last but one point here in the list, changes in runoff seasonality. Again, I've labeled it here soft fact. Why is that? There are some component in the seasonal changes of runoff which are actually hard facts. When we have increases in the air temperature and we have earlier snow melt and stronger glacier melt in the alpine areas as long as the glaciers are still around, these I would consider hard facts. But then the annual water balance in most of the catchment not only depends on snow, it only clearly depends on rainfall. And the seasonal predictions of rainfall of the climate models are not very reliable. That's why I labeled this soft fact. And yes, and the last point here, the southeast is indeed very sensitive to climate changes. This is a hard fact and is supported by those 4 different methods we have looked at. Climate change impacts on groundwater. This is a general summary. Of course, individual aquifers have their individual characteristics. In the south of Austria, a decrease in groundwater recharge is likely, a medium fact. Why? If rainfall does not change much, then increases in evapotranspiration will decrease the recharge. In the east of Austria, we may have possibly a decreasing water table, but that's not so very clear. But one hard fact, we do have the increases in the groundwater temperatures in the past, and this is clearly a trend that will continue. And you see we have here the differences between soft and hard facts. The hard facts is something where we can act with confidence. With the soft facts, we need to be more careful. My last slide, before the lunchtime break. I also have a number of conclusions on the methods. And the study was not just applying existing methods to Austria, we also came up with new methods, and I think this is also important for other climate impact studies around the world. The first conclusion, I think, is scenarios have large uncertainties. And what is generally presented in the public does not always give credit to the underlying uncertainties. You know, all these nice maps of changes in the water balance and changes in hydrologic quantities, and very rarely do we see uncertainty bounds. And if we do see uncertainty bounds, like if we run ensemble simulations of climate, then these usually underestimate the real uncertainty, because it's not only the differences between the models of the ensemble, it's also the model structure error that needs to be taken into account. So, scenarios are useful, but we need to take into account the uncertainty. And one way of doing this, and this is perfectly in line with the general scientific approach since the science has been around, is to look at alternative methods. So only if effect has been proven by more than one data set, by more than one method, then we really can give credence to the model results. And alternative methods are, for example, the elasticity and the trading space for time methods. We do not look at models, but we look at the temporal fluctuations of a number of variables and look how sensitive they are. Or we look at the spatial variations and then map the spatial variations back into the time domain. This gives an alternative view of the same processes. And if a number of methods give consistent results, then we can trust the results much more than if we only rely on the scenario approach. Second point on methods here is I would propose to focus more on why the impact studies predict certain changes rather than on the magnitudes of change. I'd had some interesting experiences where a particular study for a part of Austria, for Tyrol, predicted an increase of the 100-year flood of 150% over the next 30 or 40 years, an increase of more than doubling, right? And then when we asked the study author, why is that so? Well, it's a simulation result. And this is not what I like. It's much better to highlight what are the reasons that the floods increase. For example, snowmelt or convective storms or whatever the reason is, provides more insight, and not only, and I would submit, not only for scientific reasons, but also for management. Because if you understand what are the controls, you can give your credence to those controls which you trust more and those which you do not trust so much, and act accordingly. The third point, about being more transparent, what we can predict and what we cannot predict. And one way of tagging it is to say the facts are soft facts or hard facts. You could add uncertainty bounds if you wanted, but just as a language, just to highlight this is speculative, soft fact, may still be useful. Like, for example, how convective storms will increase or change in the next 40 years. May still be an interesting result, but clearly a soft fact. While other things, how air temperatures change and how glaciers will change, are hard facts. And to set these two things apart, I think would be a very worthwhile endeavor of future impact studies of climate on water resources. Here, the last line here is, this is the web address where you can download the full report, unfortunately in German, but there are a couple of publications that are in the pipeline on the report, both on the results and on the new methods, and I'm happy to send you the manuscripts if you drop me an email. Thank you very much.